Hello, in this video I'm going to go through a few more of the important parts of special relativity, and this will concern momentum, kinetic energy and mass energy. And I'm going to derive a few equations, but the derivations are going to be a little bit hand wavy because, as has been the case throughout this special relativity section, I've got to avoid the maths that we're not quite ready for yet. But still, there'll be some maths in it. It's just that these derivations won't be entirely robust, but still we're moving down the pathway to understanding what's going on with momentum, kinetic energy and mass energy. So I'm going to start off by moving towards E equals mc squared. So this is the most famous equation in special relativity, possibly the most famous equation in physics. And as I said at the beginning of the special relativity videos, one of the aims that Einstein had was to make all of the laws of physics valid in all of the different frames of reference. So this particularly included, well, I say particularly, he wanted all of the laws, but he really had an eye on getting electromagnetism into special relativity. So Maxwell's equations were very much in his sights. And in Maxwell's equations, looking at a photon, there's the idea of photon momentum. So the momentum of a photon, so this is a particle with no mass but still having momentum. So the photon momentum is equal to the energy of the photon divided by the speed of light. Now this gives us a quick route to getting an E equals mc squared, at least for a photon, because if you've got the momentum being some mass, whatever that means, multiplied by a velocity, which for a photon is some mass multiplied by the speed of light, and then that's equal to E divided by C, then it gives us this quick, slightly dodgy route to an E equals mc squared, and leaves the question of, well, what on earth does this m actually mean? But we've got a relationship between mass and energy. And there are, not surprisingly, much better ways of getting to, or more robust ways of getting to E equals mc squared than this, and you'll cover that when you go off to university. But at least we're getting an idea of this connection between mass and energy, and it does bring in this question of, well, what is this mass then? What is going on with mass and momentum inside special relativity? And this brings us to relativistic momentum. Now, inside relativistic momentum, and this is where we're talking about transformations again between different frames of reference, as all of special relativity is. So we're transforming between two different frames of reference and saying, well, what momentum are we going to measure in each one? If we're in frame of reference F and we're measuring momentum P, we then transform into frame of reference F prime, which is moving at velocity V with respect to frame of reference F. Then what momentum P prime will be measured in that frame of reference. Now the maths really does get too much for us here, so I'm just going to quote the result on this. And this is to make sure, because in order to derive this is making sure that conservation of momentum is valid in all frames of reference. And we want all laws of physics valid in all frames of reference. Conservation of momentum is certainly one of the big ones. So if we're doing this transformation, the result comes out something similar to the time dilation equation, where we've got our momentum in frame of reference F prime is the momentum in frame of reference F divided by our friend the square root of 1 minus v squared over c squared. So that is giving us this idea of relativistic momentum. Now this can quite easily be reduced down to talking about relativistic mass, and you see this in a lot of the older textbooks. So you'll see a lot of distinctions between m subscript 0 and m, as in our rest mass, or sometimes called invariant mass, and then our m, which is then the relativistic mass. So you'll see this in a lot of textbooks, and this is because they're kind of sneaking classical physics back in here through the back door. It's possible because the v's here, when we're measuring the relative motion of these two frames of reference, then we get the same magnitude. We're getting v in both. If we're measuring the speed of frame of reference F prime as measured from frame of reference F, then that magnitude is v. And if we measure the speed of f from frame of reference f prime, we're also getting v. So these v's cancel a lot out of these momentums, and that can leave us with m's. So what I'm getting at here is saying, well, say p dash m times v, and then we can say that p is m0 times v divided by our Lorentz factor. Then we cancel the v's, and momentum has now disappeared, and we've got an equation here relating rest mass m0 and relativistic mass m. So this historically is what people have done, and it sticks around a lot as well, because this relationship here between an m and an m0 mathematically is really useful when solving problems. It's fallen out of favor though, because it can create the wrong impression of what's actually going on in relativity though, because it's suggesting a change in structure of the object that's moving rather than changes in measurement because of what's going on in space-time. So it's moving our attention away from space-time, which is what relativity is all about. Our special relativity is all about space-time. It's not about the objects that are moving through space-time. And it's moving that emphasis from space-time to the object by suggesting that we've got an actual change in structure here in the object, is in that the mass has changed. And that isn't what's actually happened. There's no change in the structure of the object. The same with a length contraction. You know, we've got our formula for length contraction, but we haven't got a structural change in the object. We've got a change in the measurement of the length of the object due to what's going on in space-time. It's the properties of space-time that are causing these effects in special relativity. It's not changes in the structure of the object. So that's why people are more disinclined now to talk about rest mass and invariant mass and relativistic mass. You know, just think about how we get a handle on mass in the first place. If we've got an object that isn't moving, okay, we can measure rest mass on a set of scales. You know, we can use gravity to measure the mass of an object that isn't moving. So that's one way of getting a handle on mass. If we want to get mass of a moving object, then we're doing that through momentum. That's what's happening. You know, we think of our classical mechanics. We look at collisions, we look at F equals ma, which of course is to do with momentum. This is rate of change of momentum on the right hand side there. So if you've got a moving object, we only get at that anything to do with mass by looking at momentum. So momentum's coming first for a moving object. And in terms of measuring mass directly, well, we only have the mass, the rest mass. We don't really have this idea of relativistic mass. If you're talking about relativistic mass, really we're talking about relativistic momentum and then making some kind of calculation off of the back of that. So I suppose the takeaway from this is, don't think in these calculations that we're doing in special relativity that it is the structure of the object that's changing. This is all driven by space-time. So I'll leave that there for now anyway. But looking at this equation then here for relativistic momentum, you can see something else that's going on. That we know we can't have infinite momentum. That's just nuts. You know, momentum is some measure of the amount of motion. You can't have an infinite momentum. How do we get infinite momentum? Is if we're getting v equal to c, if we're getting an object that's moving at the speed of light. Now, clearly there are some exceptions to this, because we've got a photon that can move at the speed of light. So you end up, if you dig into the weeds a little bit more and your math's a bit better and you've managed to derive this in a more robust way, or in any way in this particular formula, because I haven't derived it at all, I've just quoted it, then you're saying that we can't have objects that have a rest mass moving at the speed of light. So it's ruling that possibility out. So that's something there. Right, the last thing that I want to look at then is relativistic kinetic energy. So let's do a conservation of energy equation then. We can say that the total energy that a particular object has, so well, I'm ignoring potential energy here. So we've got a total energy is going to be equal to the rest energy, as in our E equals mc squared bit, plus the kinetic energy. So we're just speeding an object up and then saying, well, that's increasing the total energy. Now the rest energy is our mc squared, because remember, we're not using these m0s now, because according to the new way of talking about special relativity, or the more modern way of talking about it, all of these m's are m0s. We're only talking about rest mass. So we've just got some m's here for mc squared, and then we add on our kinetic energy, and that is going to be the total energy. So total energy is going to be the mc squared divided by the square root of 1 minus v squared over c squared. So again, you can see why people used to talk about relativistic mass, because it really does look like it here. It's the m that's changed, apparently, in this particular equation. You can see how tempting it is to make these two m's m0s and say these are the rest masses, and then on the left hand side, essentially, we've got a relativistic mass. But still, we've got this equation here, so we can rearrange this, say that our kinetic energy is then equal to mc squared, and then we've got our 1 minus v squared over c squared to the minus a half, and then minus mc squared. So if we do an expansion of this bracket here, do a binomial expansion on that, then we're going to get mc squared, and then we're going to have 1, well, it's going to be plus v squared over 2c squared, and then we're going to have plus, it will be minus a half times minus 3 over 2 times 1 over 2 factorial. So what was that? Minus a half times minus 3 over 2. So that's 3/4 times a half. So 3 over 8. And then that would be v to the 4 over c to the 4. And then onwards. And then take off mc squared. So you can see the mc squareds are going to cancel. So that is then leaving us with mc squared, v squared over 2c squared plus 3 over 8 v to the 4 over c to the 4 plus etc. Now you can see here for small v, if v is much smaller than c, then we're going to be losing all terms after the first one, because okay, we've got a c squared on the outside of the bracket. That's fine. That c squared there can cancel the c squared on the denominator of the first term inside the bracket, which just leaves us with a half mv squared, our kinetic energy formula for low speeds. The next one, though, we're still going to end up having a v to the 4 divided by c squared. So at low speeds, we're still losing that term. So it's saying that if v is much less than c, then we've got that the kinetic energy is a half mv squared. But we've also got a calculation there for the relativistic kinetic energy. So, based on this series or by using our Lorentz factor in comparing total energy with the rest energy. So, yeah, just an interesting way how the half mv squared drops out of special relativity, as all of the stuff that we've been doing in classical mechanics really does. All of that are just approximations. They're anything which is a low speed approximation in our classical mechanics is then dropping out of special relativity. So it's all nice and consistent in that way, as you'd expect it to be for such a successful theory. So yeah, that was the last bit I just wanted to end on there. So yeah, let's run through this idea of momentum and mass energy. So yeah, the relativistic momentum is certainly an interesting idea. So keep that in mind if you do start reading around the subject and you're seeing different language being used in the older textbooks compared to the new ones, then hopefully that's helped clear up a little bit as to why that is the case. But I think this is pretty much, at least for the moment, about as far as I want to go with special relativity, because it starts getting pretty complicated pretty quickly beyond this. So I think this is good enough for now, and then you can save the rest of the excitement for your physics degree if you go off and start studying that.